Today is 20th of January, which is a class number 4 of finite element this semester. We will pick up from last time, so let me recover a little bit. Last time we worked on the bar problem. We put something that makes the function discontinuous, like the point load. Alright, so the solution turns out to be nonlinear. Well, when we have quadratic term, it's nonlinear already, but we have some sort of discontinuity, so your function looks more abnormal and it's not that smooth. The point is that we use the discretization to make the better and better fit between the finite element solution and the exact solution. You used to come up with the exact solution previously already, so you can plot out the exact solution and compare with FEM. So we start with the FEM that contains 5 degree of freedom, 4 elements. Well, knowing that the degree of freedom at the support will not move, basically the active degree of freedom are just 4. And then I requested you to do homework, and in the homework I want you to discretize the element size to be a half of the original one, which was 4 elements. So you add up the nodes. From 5 nodes, now you have 9 nodes. 9 nodes, the variables is actually there are only just 8 variables. So I think you might see the improvement of the solution by doing so. And you not only check the displacement solution, but you also use the displacement solution to construct the strain or stress solution, right? Stress or strain is the derivative of the displacement. So you use the approximation of the displacement we had, which was the linear interpolation. Once you calculate the displacement, the strain or stress, then you have one order lower. The function will be from the linear function into just the constant step function, right? So you will find that the stress solution is just like the stepwise linear. For the 1D element, your linear shape functions or linear interpolation function, they need 2 nodes, or it contains the 2 degree of freedom. For 1D problem, then you have only just 2 nodes. So today we will work on this problem, exactly the same problem, the bar problem, but we will now use the new interpolation function, which is generally the highest order of interpolation function used in the standard finite element. If we don't count the bending flexures, okay, the problem that contains the continuity of the slope, that will need the higher order shape function. But for the problem like the continuum problem without the bending consideration of flexures, this quadratic interpolation function is the highest order way to interpolate the displacement solution. Okay, so if we go to the quadratic, if you think of this one first, linear interpolation, in order to define the straight line, you need just 2 points, 2 nodal points or 2 degree of freedom. In the future, one nodal point may contain more than one degree of freedom. For example, if you work in 2D plane stress, plane strain problem, one nodal point contains two displacement degree of freedom, displacement along the x and displacement along the y. Likewise, for the three-dimensional problem, one nodal point contains displacement in x, in y, and in z. If you talk about the plate bending or the shell problem that also contains a bending, then one one nodal point may contain in-plane displacement. So in-plane displacement, if the plane is on the xy plane, right, you have in-plane displacement in x, in y, and then you will also have out-of-plane displacement, which is a displacement along the z direction, and also you have the rotation, so rotation about the x-axis, about y-axis, and z-axis. So one nodal point may contain 6 degrees of freedom. Right. So that depends on what kind of element that we are formulating, right? And then the different element type contains a different sets of displacement degree of freedom. But we look into 1D bar problem first, just a very simple one. And if you want to make the displacement field, the solution is the displacement field, right? For mechanics problem. For some application, like for an inverse problem or special application, the formulation might be based on stress formulation, not necessary to be on the displacement formulation. So the unknown might be changed. But this is the standard FEM we use, and we can find this in finite element software, right? So it is just standard. Those stress formulations for just really special purpose, for basically for the research purpose more, right? So it is very rare. But I just tell you that there is a possibility to formulate the problem using the different sets of variables that could be the stress. Alright, but we are talking about the world of the 95% thing. So we talk about majority, and displacement field seems to be what we figure out as the solution. So the displacement field that is approximate by the linear shape function, you need just 2 points, 1 and 2. As you know the value at these 2 points, you'll be able to approximate the solution elsewhere within a member, within that particular structural element. Right. But now, if you want to capture the curve like this, so we are saying that we will allow our solution to be the curve, right? And in order to do that, if you want to express this curve-like function in your interpolation function, there are many possibilities. If you use quadratic curve, you have single curvature. That's only one possibility. You come up with quadratic curve. If you go with the cubic curve, you have double curvature. Now we are talking about polynomials only, because polynomial seems to be the simplest thing simplest function, right? If you go for some other thing, it is more difficult. And as it is simplest thing, okay, polynomials is used to represent the other kinds of functions. So approximation comes in at this point. You never know if your exact solution is polynomial or not. But we think that polynomial suffice our application, and you can check the convergence. Alright, so you don't need to worry too much as we run the convergence check, and we find that the solution converges. So what's wrong? So we can use polynomials. The thing is that, okay, what polynomials? Simplest thing to use the quadratic. Why not cubic, quadratic, and higher order? Why not? First of all, yes, if you are able to capture better than just single curvature, yes, it is good. The thing is that if you go like that, if you use cubic curve, that means you might be compromising the discretization. Alright? The discretization might be less. Okay. Thing is so abstract, so I talk about it this way. So this might be the solution of your entire domain. So if you say that, okay, 1, 2, 3. So I will go for fourth order polynomial for this one. Then the element will contain like fourth order polynomial. I'm gonna need 5 nodes. Why 5 nodes? Fourth order polynomials, you will have a0 plus a1x plus a2x squared, so on so forth, up to a4x to the fourth. The a constant is to be determined. The a constant is controlling your curve. So in order to have 5 a constants, you will need 5 checkpoints. Right? So you will have 5 nodes to control your curve. Right? So you know you will need to figure out the value at 1, 2, 3, 4, 5. But look at this. If you need 5 nodes, you have 1 element, but the number of nodes increases. If you compare with the linear element, you might be able to get this. We are not sure yet about the fourth order polynomial, this one that we represent, if it's gonna match or not exactly. Or if you come up with something else like quadratic, you might be able to get this and to get this, because quadratic curves gonna need 3 checkpoints. So basically, if you refine your mesh, like for the linear element or even for quadratic element, if you use the linear interpolation function, you get this. If you use quadratic, you'll be able to get this curve. For this one, also you can get this curve. Why? Because the curve right now, if the discretization is good enough, the mesh is not too coarse, you'll be able to capture the single curvature curve nicely. And for here, maybe you might not get this curve. Originally it was double curvature. This curve here, you can see that, okay, it seems to be one and another curvature, but quadratic one might not be able to pick up. Well, basically that means you might need further discretization in some area like that you have the large and abrupt change of the solution. And the last one, okay, just single curvature curve, that might be captured very nicely also by the quadratic curve. So you can see that there is no need to go up for higher order functions. So you might have some sort of question, why Why not? Okay, why not? First of all, I told you, you will not need just only 1 or 2 points, nodal points. You will add more nodal points in your higher order curves, higher order element. Right? You need more nodal points or checkpoints for the degree of freedom. That means one element gets larger in a mathematical point of view. If you have 5 DOF, you will end up with 5 by 5. Now you have some idea, you know that the band of the matrix will be wider. Compare with the same number of node discretization. Alright? If you have the same number of DOF but you use linear element, you end up with just this wide band, 2 equals to 2 or 3. For 5, when you connect to another element, then your band, the widest part is equals to 9 over here. Other points, it is just 5, whereas 2 to 3. Or if you have quadratic element, you have 1, 2, 3, 1, 2, 3, 1, 2, 3. Quadratic element is gonna make the stiffness matrix look like this. So 3 and the widest part 6. That means much more storage will be required for that high order element, and then it turns out to be cheaper to discretize more, add more checkpoints rather than just trying to use higher order element, right? Having more checkpoints seems to be the better way. Alright, so then I'll clean this up. Then we come to the 1D, which is an 3DOF element, or the quadrat that use the quadratic shape functions. So in order to define a curve, told you, you have 1, 2, not enough, 2 points, just enough to define a straight line. If it is the quadratic curve, you need another point. So in total you have 3 checkpoints. These 3 checkpoints are associated with these x1, x2, x3. So how does the shape function of associated at each checkpoint, how does it look like? So for the checkpoint x1, let me ask you first, what is the characteristic of the shape function? It should give us the influence of the displacement at the point where it is associated with, right? It gives the influence. Previously, it is very easy to figure out, it was linear. So you have the linear variation of the influence of the shape function from 1 at the point where it is associated with to 0 where it is another point which is controlled by another person. So for quadratic shape function, it's gonna work the same way. You will get the function that exhibit the influence equals to 1 at its nodal point and 0 at other nodal points. So let's take a look at the first one, the x1 phi 1 over here. Our phi 1 is got to be x minus x2, x minus x3. What does this mean? X minus x2, when the x value is equal to x2, you're gonna get 0, or equals to x3, you're gonna get 0 from another parenthesis. So this multiplication gives you the OR, right? It could be x2 or x3, then you get 0. Now, in order to find, this is not the complete function yet, because we satisfy the requirement of being 0 at x2 and x3, but we have not satisfied the requirement to exhibit the value equals to 1 at x1, right? So you will need to substitute the x1, right? Once you substitute the x1 in there, you're gonna get x1 minus x2 and x1 minus x3. This is your value. What is the next? You do not want this value. You want 1. So the whole thing will be divided by this one. So once you substitute x1 in there, then you get the influence equals to 1.0. Likewise, when you work on the phi 2, you're gonna get the x minus x1 times the x minus x3. You need the value to be 1 at the point x2, then you divide it out by x2 minus x1 and x2 minus x3. And likewise for the phi 3. So basically your approximate displacement will be represented by, again, the formulation we are talking about right now is the formulation in the physical coordinate. We are talking about the formulation of these functions using x, which is physical coordinates. Later on, we will map these physical coordinates into the numerical or the local coordinate. Physical coordinate is the global one, global coordinates. So you have u1 phi 1 plus u2 phi 2 plus u3 phi 3. Given that the u1 will be here, u2 will be associated like this. How does the shape function looks like? Each function One, two, three, and okay, this is at the middle. So let's start with the first one. At this point, the function value is equal to 1.0. it. So here is your first function. Okay. Equals to 1 at node number 1, equals to 0 at 2 and 3. Now the function number 2, let me copy this one now first. Resize, convert, delete, convert, okay, cancel, we don't want it, convert, resize, can it be flipped? No function flip. Color, convert, cut, copy. Okay, I just no, and delete it then. Number 2, and the last one, V3. Difficult for my hand to draw this. Oh, right. V3. So we will do this. We will solve the problem last time using the quadratic shape function. Alright. Class number 4, page 2. So I will borrow the figure here. Just gonna copy. So our problem is this one. I gonna use the same discretization you have from linear interpolation function. So it is quite fair, right? If you want to compare linear to quadratic, and if you use the same discretization, I mean same number of elements, then you might not end up with the same number of degree of freedom. I think the fair comparison will be based on the equal number of degree of freedom for the whole system. So for linear element, if you can break into 4, you have 5 degree of freedom in total. If you use quadratic element, you will have just 2 elements and end up with 5 number of degree of freedoms. So basically, the stiffness matrix, the size are identical for linear and for quadratic interpolation, because I fix the number of nodal points. I don't fix the number of elements. That means the computational cost seems to be close. I said seems to be. It is not equal because the band of the matrix are not identical, but the number of degree of freedom are identical. Alright, so when you put it in the solver, sure, you find that the computational time might be more when the number of degree of freedom are, even though it is equal for the number of degree of freedom, but still the non-zero terms in the stiffness matrix are not identical. So the solver, which is the linear solver that people use in the finite element business, the linear solver collects non-zero entries. So it has more non-zero entries to collect. It takes more space in the RAM. Alright, in order to solve this problem. But the best comparison will be through this. You cannot get better anything. Nothing. Okay. So first of all, we discretize the problem into two elements. Element number 1 and element number 2. So the displacement approximation within the element number 1 is equals to u1 phi1 plus u2 phi2 plus u3 phi3, whereas this approximation is equals to u3 phi3 plus u4 phi4 plus u5 phi5, this way. So we will need to use the derivative of shape functions, right? So first of all, I think we will expand all these out. Basically, if we are not expecting, okay, we put everything as it should be. So for the u1, you're gonna multiply by the x minus a quarter L and x minus L over 2. If you substitute 0 into here and there, you're gonna get minus L over 4 multiplied by minus L over 2. You end up with L squared over 8. So you're gonna multiply by 8 over L squared in order to normalize the value of this function to 1 when the x is equals to 0, plus u2 x minus 0 and x minus L over 2. You got to multiply by minus 4 over L squared. You substitute L over 4, 16, not 4. You substitute L over 4, so L over 4 minus 0, you get L over 4, and L over 4 minus L over 2, you get minus L over 4, so you get minus 16, right? Minus L squared over 16. So you got to multiply by minus 16 over L squared. The last one, u3, x minus 0 and x minus L over 4. So you're going to substitute the L over 2 into x. You end up with L over 2 multiplied by L over 4. So you need 8 over L squared. Keep expanding it because we're gonna need the derivative of this displacement approximate solution of u. So you have, let me take out the 8u1 over L squared multiply by x squared minus L over 4 add up with minus L over 2, you get minus 3/4 L x plus L square over 8. And then minus 16 U2 L square of x square minus L over 2x x square minus L over 2x 16. Alright, and then 8u3 over L square. That is what? X square minus L over 4x and then if you want to take derivative of u with respect to x, you'll be getting to x minus 3/4 L minus 16 u 2 L square to x minus L over 2 plus 8u3 L square to x minus L 1/4 L. Oops. Whereas this side yeah, I'm so lazy to do this. u3 the shape function number 3 in the element number 2. Let me check if it is going to be the same. It is for the range where the x is greater than L over 2. So this shape function for u3 for the element number 2 should exhibit the value of 1 at L over 2, 0 at 3/4 L, and 0 at L. So we will cast the different function x minus 3/4 L and x minus L. Right? And then plus u4 x minus a half and x minus L. I will put in the coefficient a little later, L minus 3/4 L. So for the first one, this is going to be 8 over L square. This is going to be minus 16 over L square. It's going to be 8 over L square. And that's gonna make 8u3 over L square x square minus 7/4 Lx plus 3/4 L square. minus 16u4 L square. 16u4 L square, you get the x square. What is the next one? 1.5. That makes 3 half. And the last one, plus L square over 2. Plus 8u5 L square. We're gonna make x square 1/2 and 3/4. 3/4 is 2. L over 2 is equals to 2/4. So that's minus 5. Right? 5 over 4 L x plus 3L square over 8. Let me highlight you the pain. Let me do that. You find that what we are doing right now, is pretty much painful to me and to you, mostly to me now, because I'm running the calculation, you're just copying. The point is that the repetition of the formulation is required when you do the global coordinate formulation. You move to the next element, you need to formulate again and again and again and again. But actually you know that for this super easy bar problem, the stiffness matrix is gonna repeat. Well, later on, if the geometry is not constant, but again, the core of the stiffness matrix is going to repeat. And that is the same for the different kinds of member, like 2D member, 3D members. If you have the identical size, identical geometry, stiffness gonna repeat. Or if the geometry and the size may not be identical, but the formulation, the procedures will be repeating, you do not have to reformulate. The formulation of the shape functions, which is carried out every time, is the pain that we would like to get rid of as soon as possible. Well, later on you might have something to do, like some integration needed for the 2D problem when geometry are not the same. But you do not have to come down to the x and y. You are in local coordinates, so your local shape function, they do not need you to re-establish the functions. Same functions to be used, but applies on the different geometry, right? That's gonna save you a lot of time. And the concept of finite element is to come up with the algorithm that is the most computer friendly. And reformulation like this is not friendly to the computer. So that is the issue. Okay, we will go through this pain once, and once we're done with that, well, you will expect homework, because I will not let you just get away with this that easily. Okay, at least you will need to experience some of this pain, just a bit, and then you will love the local coordinate formulations, right? So du dx is going to be 8u3L square 2x minus 7/4 minus 16u4 L square 2x minus 3 half and plus 8u5 L square 2x minus 5 quarter L. For the meantime, I think we will finish up the let me clean up the grass. I will list out all interpolation functions and the derivatives of the phi I do it phi 1, okay, which is superscript d phi 1 dx is equal to copy from here. Okay, I think it is faster to do it this way. Just copy everything from here and paste there and then put it okay. Alright, d phi 1, I'm gonna take this whole thing up and erase something out later. So I'll list off d phi 2 dx, d phi 3 dx, d phi 4 dx, d phi 5 dx. Alright. Put them in. There'll be something to correct, to clean out, but I'll do it soon. Okay, I'll clean this part first. Okay, and I'll come here. So if we take the derivative of the shape functions, I clean out the u. And this is good when x is greater than 0 and less than L/2. It is good for the whole element. And here is good for x is greater than L/2 and less than L. So the phi 3 shape function for the nodal the displacement number 3, it is on the boundary between two elements. So the function that controls if you are in the range where x is one range, you have one function and another. Now you have all the functions. It is time to come back to page number 3. Come back to our weak formulation. So we have the W du dx W times du dx, the whole thing is evaluated from 0 to L minus integration over this domain of the EA du dx dw dx dx plus integration from 0 to L of f w dx equals to 0, and then we will evaluate this first of all. The W is equals to phi number 1. So with phi 1, the term in here is not going to appear. The boundary condition, when it is enforced, you do not have anything out of this first term. Alright? I will not expand it out, because once you expand it, and then you're going to find that you cross out all the way to 0. So we have the part over there from 0 to L over 2. The part from L over 2 to L, you will find that the W is 0, right? So if the W is 0, then we do not have to evaluate that integral. Alright, so EA, and then we take the du dx for L over 2.
The weak formulation, I think the first term should have EA.
Or EA du dx, yeah. Switch it around a bit. So du dx, we go back here, and this is our du dx. Yeah, so much fun. So I put it here. I put the big bracket, and thank iPad, thank Apple. Without this, so this is the du dx for this domain multiply by dw dx do not buy an iPad because you just want to do this homework, right? Last couple of years people went through the FEM course and find the homework like this, and then finally I think Apple should pay me the sort of commission or some percent, because I make their sale, I improve their sale, yeah, at least a few iPads in the class, yeah, in this class. Right, but we are not going to do this like for many times, all right? You can just continue with your paper. What next? Dx. Plus integration from 0 to L over 2 like before. Yeah, we consider only domain. Then F multiplied by W. The W is this one. Oh no, this one. Yeah, now we get the W. We just need to remove the U1. That's it. We get the W dx equal to 0. So much fun in there. This is V1. Right, let me take a deep breath before starting all of this. Minus E A times 8 over L square. Take this whole thing outside. Integration from 0 to L over 2. In the bracket U1 to x minus 3 quarter L, the whole thing square, okay. Not just 8 over L square. Let me EA 8 over L square, square it up, and we have this 8 over L thing from here and 8 over L from there, right? You have double. And next, minus 2U2 to x minus L over 2 times 2x minus 3 quarter L plus u3 2x minus L over 4 and 2x minus 3 quarter L. There you go. Dx So let's finish this up first. I think another integral is very easy to deal with. Let's fix this one. U1 4x squared, and then what? 6 12 over 4, which is 3lx plus 9 over 16 L square. Very tedious. Let's check. 2 of this, 4, okay, yeah, 3, just the 3 remaining, and then the last piece square up, 9 16 L square. Great. Minus 2u2 4x squared this and this, so minus lx and minus 3 over 2 3 over 2 and 2 over 2, that makes a 5 4, right? 5 over 4 plus L 3 L square over 8 and plus u3 4x squared. Maybe next year, after this course is digitized, ask the student, okay, it will be done this way, and then the rest you watch on YouTube. I will not do it again. I have been doing this for 10 times already, and I don't think I have a good reason to repeat it. So I better talk about other things, and then okay, you watch this one. Unbearable. Continue. Here L over 2, and there. Hey, why is it the same? Oh, L over 2 and okay. So that makes what? L over 2 and 3 over 2, so 4 over 2, which is 2, right? Minus 2 Lx plus 3L square over 16. Yeah, which one?
5 over 4 should be 5 over 2.
5 over, huh? Which one?
The minus 5 over 4 will be 5 over 2.
Oh, 5 over 2. Thank you so much. You are preventing us from the catastrophic disaster later when we cannot find out what goes wrong. Thank you. Dx. Huh? Yeah, it is. Yes. Now, how to do things strategically. You have x squared, you have x term, and then you have just a constant term, right? If you integrate the x squared dx from 0 to L over 2, what do you get? that is L square over 4 multiplied by a half, right? No, L cube. Okay, you're gonna get x cube over 3, 0 to L over 2, which is L cube over 8, right? And then multiply by 1/3, that makes the L cube over 24. Okay, this is the first guy, L cube over 24. Let me note it out. L cube over 24. How about the x term? X term turns out to be the x squared over 2. X squared over 2 turns out to be L squared over 4 multiplied by a half, which is L squared over 8. And L over 2. That does not need any special calculation. Alright, drop in. So yeah, we are dealing with just one element evaluated with the first test function, first W. How many W do we have? 5, right? 5. I will not finish it up today, but you will. But you will. Okay. First one, U1 multiply by 4 times L cube over 24 minus 3L L square over 8 plus 9/16 L square L over 2. So later on I will not list the L. I will put minus 2 U2 L cube. In there I have 4 times 124 plus 5 over 2 times 1 over 8, right? Plus 8 times 1 over 2 plus U3 L cube 4 times 124 minus 2 times 1 8, oops, running out of paper, plus 3/16 times 1 over 2. Let me just do it this way to save the space such that it is easy for us to see. 3 over 8. I squeeze in the space a little bit. Multiply by 1/8, multiply by 1/2. A little stingy with the space. I'll take this to U2. I erase that L. I get out this over here. Hope that you guys pick up the possible errors already. If you have one, then that's gonna be fantastic to come back and go through. Okay. Nice. Let me cross out. Not here, not now. calculator. Oh, what are these? 16 minus 38 plus 9 over 32. So the common factor might be the 64, right? Oh no, 9. Right? 9. And then minus. No. That is 54. Well. Then what was supposed to be? 96.
7, 96.
7 over 96.
7 over 96.
Total.
You done?
Total is 7
Okay. Great. 70. 7 over 96. Okay, good. Yeah. To use the calculator. How about this? That should include 2. Is that good to my brain? I'll become one 6, 5, 16, right? 3, 16. So 8, 16, which mean a half. Add up with 1, 6. I get 7. No. A half and 1, 6. 4, 6, right? A half and what? A half, which is 3, 6. 4, 6. 4, 6 is 2/3. So I get 4/3, right? From here. 4 over 3. Last one. 1, 6 minus 1/4 plus 3/32. Okay. 1, 6 and 1/4. That's a 4 minus 6. That minus 2 over 24.
1 over 96.
1 over 96. Okay. Is there anything missing in the if we take 8, 7, 4, 1. If this is all 96, then it's got to be Is there anything missing here? I find it. This is minus. Yeah, number is not so familiar to my eyes. 5, 16 plus 3, 16, right? 5 and 3 minus 2, 16 minus 1, 8, 1, 6 minus 1, 8, right? So it is 2 over 48. 2 48 turns out to be 1, 6, right? 1 over 24? I got 1, 6. Is it 1, 6? 112. Did you multiply by 2?
Yes.
Okay.
2 over 48 multiplied by 2
2 over
48.
48.
1 over 8. 124.
4. 1/6 first, right? 5/16, 1 second, 3/16, 5 turns out to be 2/16, which is 1/8. 1/6 minus 1/8, which is 2/48. Multiply by 2. Okay, so 4 and 48, 124. Huh? 112? Oh, 448. Yeah, 112, 112. Okay, alright. 112. So 112, 1 over 12 multiplied by 8 over 8 turns out to be 896. Alright. Okay. Looks good. The number for the quadratic shape function stiffness matrix, which we should see 7, 8 and 1. Yeah. Okie dokie. How about these people here? I will then do this. So it is 8 square and this to the 4th, right? So this makes and then 8 here, cut it out first. The first 8 make 96, 12, 12, 12. The next 8, we cross it out, you leave just 3. So this is 3 as well. Hey, what? 2, sorry. Okay, so we take 4 out and then cross this out and then 3. So let me express this in the next page. Minus EA over L over 2. EA over L over 2. And then 7/3 U1 minus 8 third, right? U2 plus 1/3 U3 equal and then plus this term 7, 8 and 1/3. Or is it 7 and 16? Is there anything left to be correct? Let me see. Let me find out. Oops. Very easy these days to pick up something from the last year. Oh, this is equation number 2. Equation number 1, you better get okay. 7, 8, 1/3. Okay. Yeah. Oops. Okay, so that's the second line. Alright, so this seems to be correct already. Now let's take a look at the integration here. So we have f multiplied by 8l square. Integrate x square again you get what? L square 24 minus 3/4 L that's L cube, L square over 8 and plus L square over 8 times L over 2 like this. Turns out you get FL8 is there, and 124 minus 1/16. So 116 is 232. We get minus 132. Minus 132, 124. 96. Then can we get 96 out of this one? 24. Yes. Okay. So 496 minus 3. Right. 96. It is 196. So 8 divided by 96. It is 8 over 12. Just that, right? FL over 12. FL over 12. Yeah. FL over 12 equals to 0. Basically, FL over 12 is, in other words, F times L over 2 divided by 6. Alright. So you will find that the distribution of force is no longer linear. Like the linear element, you have 3 points. The length here is L over 4 and L over 4, right? The total length is L over 2 for this element. The node that is associated, we are evaluating at this node. Okay, so the part of the force that comes to this node, if you use linear distribution or the concept of tributary area, it will be L over 8. So your force will be FL over 8, which is not FL over 12. But that is based on the linear distribution. So you distribute the part half to there, half to here, half to here, half to there. So if you do it that way using tributary area concept, then FL over 8, this is FL over 4, this is FL over 8. You add them up, you get FL over 2. For this one here, you will end up with FL over 2. The force will not go anywhere, will not leak, okay, cannot disappear. But the thing is that the distribution and the way we locate forces to each individual node will be different from that concept. So that's why you get this FL over 12. So basically it is the 1/6 distribution of the total force within this member come to the left node. Later on you will find the middle node, it's going to be like 2/3 of the whole distribution. Now you have 1/6, right? Middle one will take 2/3 and another one will be 1/6 as well. So that will all adds up to 1. But you will see. equation number 1. Now we are done with equation number 1. We are going to do this. W equals to phi 2. We have 10 minutes. So I will just use the iPad Magic to take all this Can I get the sort of like sponsorship from Apple during the lecture on the YouTube? I gave the lecture for a while, and then advertisement is coming up soon, and then Apple iPad, make your life easy, and then I'm gonna get paid from that. It's a good marketing strategy. The point is that I'm gonna use this. Oops, not this one. Oops. I'm gonna replace that old thing by this one. And this one, I'll take the this one. Let's just take out the U2. This is not phi 1. This is phi 2. And this is d phi 2 dx. So again, take a deep breath. Let's finish up the easy part first. The minus 16 over L square F. You integrate x square, you get the L cube over 24 minus L over 2 times L square over 8. So that makes the L cancel, right? Minus 16 FL, 124 minus 116. So this is 248 minus 348. That makes minus 148. Minus 148 multiplied by minus 16, then you get FL over 3. Okay, just the mathematics. FL over 3 is equal to FL over 2 multiplied by 2 over 3. So this piece here is F times L over 2 times 2/3. You get the 2/3 fraction. Easy piece done. Alright, the difficult piece is coming up. Earthquake after this one, right? Who cares? Minus EA. I take out the 8 multiplied by minus 16. Okay. 8 multiplied by minus 16 over L to the 4th. Okay, bring them out. And the inside from 0 to L over 2, the domain is still the same as before. Fantastic. 2x minus that thing. Okay, so I get you 1 for x square. 3/2 and L. 3/2 and L. It's gonna make it minus 5/2, right? Plus, oh no, minus, oops. Oh yeah, plus, okay. So plus 3/4 and 1/2 plus 3/8 L square. This is for U1. For U2, minus 2 U2. And in the bracket 4x square L and L, so it makes what, L and L, what, L add up with L, so it's just 1, right? 2xL over 2, so plus or minus 2lx plus L square over 4. Boop, boop. Okay, 2lx plus u3 4x square, a half, that makes 3lx, right, plus L square over 8. Please use your eagle eyes to pick up if there is anything bad around here. Okie dokie. U1 4. I don't write the L. 124 minus 5 over 2 multiplied by 1/8 plus 3/8 multiplied by a half minus 2u2 4 and 124 as well, minus 2 1 over 8 plus a quarter 1 over 2 plus u3 4 124 minus 3/2 of 1/8 plus 1/8 and a half. Whoa, right, doable, still doable. Right, 1 6 4 124. Thank you. The next. 1/8 and 1/8, so get just 1/8, 1/8 and 1/6. That's what? This is 1/8, this is 1/6, so 8, 248, 248, 124, 112, right? 112, and then 1/6 minus 316 minus plus 116, so that makes 1/8. Okay, 1/6 minus 1/8, which is 248, 124. Right? Let me know if something is incorrect. Multiply by minus EA. The L cube cancel out this thing and we have just L. We have the 8 and the 16. Okay, I will take 4 from the 16. So I have minus 4. No. I clear out the 8 first. One second. What will be the 6, 4, 6, 3, 6, right? 8 turns out to be 2. Multiply by minus 16. Let's put the minus 16 in there. If I push the minus 16 in, okay, right now I have the EA, I have L over 2, which is beautiful right now, and I put in the 16, so I have the minus 16 over 6 U1 plus 16 over 6 over 3 U2 and minus 16 over 6 U3. That will be made into the better look for these guys to be the 8 over 3 and 8 over 3. Okay. Alright, good. Add up with 2/3 of F multiplied by element length, which is L over 2. But the reason why I arrange everything in this form is to highlight that the element size is L over 2. So when you change to the different kinds of element, you just take the element size and put it back in here, right? And this is also very useful if you want to compare yourself with what you learn in direct stiffness approach and when we learn computer method in structural analysis, because we do like what, EA over L, which is the element length, and then in the bracket, in the stiffness, then you have the numbers in there. So we do all of this so that you can compare if you end up with the same thing you had before. Well, of course, before you had only just one kind of element, linear element. In finite element course, you have quadratic bar element, right? Which is not necessary for the general structural engineering point of view, because you make the truss analysis, you do truss analysis, you you don't have point force applied in the middle of the truss. You don't have any distribution in the middle. So the truss element in SAP, it just probably contain only just 2 DOF. That's the reason you don't end up with the case where you need the quadratic interpolation, because you have displacement here, you have displacement there, 2 points in between. It will be linearly varying, right? But for finite element point of view, maybe you end up with some more sophisticated analysis than general structural analysis. So this might be useful for you. You might run wave propagation problem. You might study the pi with the distributed spring problems, and so on and so forth. So you expect the solution to be different from what you learned before, right? In your truss problem, you don't have something like this apply in between the truss member, so it is not necessary to go this far. So if you want to use the quadratic bar element, then you might need to come to the full-fledged finite element software like Abacus, ANSYS, Athena, LS Dyna, so on and so forth. You name it. Okay, many programs, many software, but not available in software like SAP, which is mainly for general structural analysis purpose. Okay, well. So what? So we run out of time right now. Then what is your contribution? Let's talk about it. Your contribution from this point, you can do this by yourself. I shouldn't use you can, right? Because that sounds like very voluntary. This is involuntary because you are required to do. So W equals to phi 3. For this, you have this part from L over 2, and also this part from L over 2 to L. So the first one is the du dx for element number 1 and du dx for element number 2, right? Likewise, for the dw dx, you can see that your d phi dx or dw dx, this is for element number 1 and this is for element number 2. So you will put the different functions into this point. That point force will pop up here just like when you work on the linear element, because the W value will be equal to 1. Alright? So point force will pop up. Regarding the force, you have double. So this will be like 2 multiplied by that, but F L over 2 over 3. Because this node has the contribution from 2 elements, so where you will get will look like this. It is like when you combine the stiffness matrix and combining the force vector. So the point or the degree of freedom where it is in common between 2 elements, you will get the the accumulations of the force, right? So phi 3, that's all for the phi 3. Then phi 4, go through quickly, and phi number 5, right? Then what do you get? You will get the overall system of equation. Solve it, and then write down the displacement solution. So displacement solution, how do you express your displacement solution? I shall talk about it a bit. You have two elements, one node, 1 2 3 4, 1 2 3 4, 1 2 3 4, and 1 2 3 4. Here is your so in order to express the value on this curve, you need to break it down into sub-points, right? So break it down into 20 points. Previously, you did the linear interpolation. You need just 1 point on one end and another point. In total, you have 2 points. You draw the straight line, done. Now you want to show the curve. To show the curve, you need to put like many straight line portions connect together, and that's gonna look like the curve. So you evaluate not 20 points, 21 points. (21 points) mean 20 elements. Yeah, 20 elements. So you can figure out this is 0. This is what, L over 2. So you break the element length L over 2 into 20 pieces. Then you get many points. So x value from 0, from 120 of L over 2 to 20 of L over 2, 320 of L over 2, and so on. You have the phi function multiplied by u1. You have the phi 2 u2, phi 3 u3. u1, u2, u3 are from your finite element solution because you solve the whole system. So you get u1, for example, u1 multiplied by your function x minus x2, x minus x3 divided by that x1 minus x2, x1 minus x3, and you substitute the x value. Okay, x value is from here. Okay, then you get this value. Do the same thing for here and there. Add them up. You get u. Okay, and continue down this way. So this is u associated with this x value. This is the next u associated with the next x value. So you'll be able to plot, when you plot, connect two nodes using straight line. Do not use the curve to connect. Okay, just use the straight line. You finish the first element, then you will have to construct the same thing there again for the next element, because you are using the different interpolation function. So your x value will be right now 0 plus L over 2, right? and that 120 multiplied by L over 2 plus L over 2. Your x start from L over 2 and onwards. Then you have V3U3 plus V3U3, V4U4, V5U5, and then you get the new U. You can plot this part there. Done with displacement. Show it along with your exact solution. Also copy the finite element solution for linear interpolation function and put it in here. So linear interpolation solution, exact solution, and quadratic, of which the number of degree of freedom are identical. You don't need to put the 8 elements of the linear in here, right? Just compare like this first. Furthermore, okay, you don't like this furthermore word. Furthermore, I also need stress distribution. So stress distribution come from, or strain distribution, du dx. To get this du dx, u is equal to u1 phi1 plus u2 phi2 plus u3 phi3. So the du dx is equal to u1 is the constant, don't mess with it. Then you have d phi1 dx plus u2 d phi2 dx, and so on. So you're gonna plot this like here. You have u and then multiply by the function d phi dx. So calculate d phi dx. I gave you d phi dx already up back there. Go back, get it, but then you plug in the different x value into the d phi dx. Alright? And then you'll be ending up with the du dx. So you get u1, which is the displacement solution obtained from the equation solving, multiplied by d phi dx, evaluate at a point x. Likewise for 2, for 3. Done. Sum them up, and then you get stress distribution. That is going to look like straight line. But just verify this. Then you can plot stress or strain. Last time, what did we plot? Stress? Strain. Alright, stress. Okay. Plot stress for this one then. So stress is just matter of fact you multiplying by the E, right? So that's it. Okay, so plot stress, compare with the previous stress from linear element and exact solution. Alright, so that's the two final outcomes we have from this homework due Thursday. Alright. Okay, I'm gonna upload the video of this. You should start working on this